All right, I'm going to be spot checking these packets. Hopefully questions won't take as long as yesterday. We'll see. Maybe they'll take longer. But let me go ahead and open my calculator. How many of you guys had to use your calculator at some point last night to solve something on this packet? Okay, so I'm opening my calculator just in case. I'm asking for attention. And if you are bored, you can be working on the new packet because you have plenty to work on. We will talk about spring break logistics towards the end, and I am hoping I can spot check while you guys start working on the next packet, which is the last BC review packet, which is number 3. Which I really apologize. Do you guys notice that you did number 3 second and now you're doing number 2 third? So really it is number 2. Go team. But it is the third of our reviews. And what's the topic of that one? Logistic and Euler's method. Woo-hoo-hoo. Okay, let me change my mode to polar, if I can get there. All right, guys, let's start with multiple choice. Let's not go straight to FRQs. On the multiple choice of the odds specifically, because evens are technically bonus. Evens are technically bonus. Whew. Do we have any questions on 1 through 5? Let's start there. 1 through 5. Any questions? We're going to go in a somewhat organized manner. No? Okay. Any questions on 6 through 10? Which one? Yeah, 10, 9, 6. So starting at 5. No, I know, but I already asked for 1 through 5. It's okay. No. Number 5. Let's start there. 5, 6, 9, and 10, and then we'll see if we have any more. Number 5 was a graphing calculator one. However, to be honest, you should have kind of known what this graph was anyway. Why? What kind of graph? What kind of polar graph would this be? A four-leaf petal, right? A 4-leaf rose, or a 4-petaled rose, however you want to put it. And it has what kind of symmetry? Odd, which would be the same thing as cosine is pi over 2, right? It'd be polar axis symmetry. Yeah. It'd be polar axis symmetry. I think it actually ends up having both symmetries. It doesn't really matter, but because it has sine. The graph curves only 2 petals on 0 to 2 pi. True or false? False. How many petals should it have? But wait a minute, maybe they're trying to trick us and they gave us a weird interval, 0 to 2 pi. Will this thing complete? Yes, and actually, how fast will it complete? In pi, because it's going to go between 0 and 2 pi by the time it gets to pi, right? The sine values? Because if you plug in pi, it's 2 pi. It's going to go in between. So it's actually going to finish in pi, and then it's going to graph over itself again to get to 2 pi. So yeah, it's graphing those 4 petals twice, so 1 is no way Jose. Number 2. If a particle is moving along the curve in the direction of increasing theta, which means just the normal 0 to 2 pi increasing theta, is traveling towards, we've talked about this. What dimension is it talking about? What quantity is it talking about if it says towards the origin? Is that x, is that y, is that theta, or is that r? R. R is how far out from the origin. Not horizontal, not vertical. R is how far out. So what it's asking is, towards the origin is r prime of theta negative at pi over 6. Because then r would be decreasing. If r is decreasing, the particle is moving towards the origin. Does that make sense? So what do we have to do? R prime of theta. Why r prime of theta? Because it says increasing theta. So we can be taking the derivative with respect to theta, not like with respect to time. So we don't need to go to x, don't need to go to y. And so it would just be, r prime, 2 cosine 2 theta. Plug in pi over 3, we end up with 2 cosine of 2 pi over 3, right? Oh, pi over 6, pi over 6. Sorry. I thought we were plugging in pi over 3. So plugging in pi over 6 times 2 would be pi over 3. Sorry, I forgot this was pi over 6. I thought it was pi over 3. So plugging in pi over 6, we get pi over 3, which is going to be a positive. True? So this is false. Because my R would be increasing, not decreasing. If you guys look at process elimination, the final answer is B, number 3, but let's look why. Suppose that a particle is moving along the curve for t greater than or equal to 0 in such a way that t equals theta. Ooh. At t equals theta equals pi over 3. The particle is moving towards the origin at a decreasing rate. Ooh. Towards the origin, r prime less than 0. At a decreasing rate, r double prime less than 0. True? So, my angle is now pi over 3. Plug in pi over 3. Can't I now say 2 pi over 3 cosine is negative, so this is true? And then r double prime, wouldn't I just need to go ahead and do chain rule again, and r double prime would just be negative 4 sine of 2 theta? And if I plug in pi over 3, sine of 2 pi over 3 is a positive. Positive times a negative is a negative. Check, check, done. So, towards or away from the origin, which quantity are we looking at? R. That's very new with polar. Okay, I heard you guys ask about number 9. Is there any question before 9? 6. Thank you. Is this the one, Katrina, you and I were doing? Okay. I made a grave mistake at the very beginning of this problem, not visualizing the graph. I think that makes all the difference. Look at him. Cosine of 3 theta. What kind of graph is he? A rose, a 3-petaled rose. So if they want me to find the area inside the polar curve, if I find 1 petal, I can multiply by 3. How can I find petals of a rose? Zeros. Because every time it completes a petal, isn't it hitting another 0? However it graphs, it passes through the pole and it makes a new petal. So therefore, if I set this equal to 0, I would go ahead and pretty quickly, cosine of 0, aka 3 theta is equal to 0. Sorry, cosine is 0. 3 theta should be equal to, at pi over 2, 3 pi over 2. We could keep going to 5 pi over 2 if we really wanted to. But we still have to divide everybody by 3. So theta is equal to pi over 6, 5 pi over 6.
That's a 5 pi over 2. That would just be pi over 2.
Thank you, thank you, thank you. Pi over 2. That was my 5 pi over 6. Yeah. Okay, now hold on. There's a lot of stuff going on over here, right? How long would it take for this function to graph its 3 petals? Kyle's thinking 2 pi is a normal rotation, right? And then divide by 3 because it's going 3 times faster. Can we put it that way? So 2 pi over 3. The dilemma is does it really finish that fast? It might. The reason is there's one of the bounds that goes between 0 and 2 pi, right? So then, don't you think a lot of kids might have just said, like, oh, no big deal, the area inside, so 1/2 r squared, and then 0 to pi is the period. That's why you see why letter C is what it is. The rest of them are either going between 0 and pi, or they're going between, I don't know, something and pi over 6s. Here's the idea as far as finding 1 petal, and not having to worry about the 0 to 2 pi and the period, and having to actually graph it all out and see how long it takes. Couldn't we also have put plus or minus up here, guys? If we did plus or minus, couldn't all these have been plus or minus? Question, starting at 0, what's the closest interval to 0 where 1 petal will complete? Doesn't a petal start at 0 and end at 0? So, couldn't I say negative pi over 6 to pi over 6 is 1 petal? Would that be true? Because it'd be from one 0 to another 0. So from 0 to pi over 6 is going to be half of that petal. From negative pi over 6 to pi over 6 is going to be a whole petal. So we could go ahead and set up and be like, oh, well, a whole petal will be negative pi over 6 to pi over 6. there are 3 petals. I need to multiply by 1/2 of this guy squared. So cosine squared of 3 theta. Does that match letter B? 3 petals, yeah. The right range, yeah, but where's the 1/2? But doubling the half, that shouldn't be a 3, right? Ah, you guys are thinking of which one is the right answer, not defending a wrong answer. Got it. So what if you changed this and said, wait a minute, the symmetry is there. There's going to be symmetry between negative pi over 6 and pi over 6. What if you only went halfway? If you only go halfway, there should be a 2 in front. And the 2 in front, think even symmetry, will cancel out the 1/2. Hence why the answer is even symmetry. If you cut the bounds in half, you're going to have to double it to get the entire first petal, then multiply by 3, doubling the half. There we go. 3 times the integral from 0 to pi over 6 cosine squared. Sorry, cosine squared of 3 theta d theta. Okay, number 9. Was graphing calculator. Technically, you guys could be trying to find intersections by hand, but don't you see all the decimals that are going on, right? And so if we go ahead and graph my 2 minus 2 sine theta, just because they said we could, so why not visualize it and not have to stress about it? My other one was 2 cosine theta, right? Let's delete. Got it? My window, just to see what's going on. That should be all right. I probably want to zoom in. Some of you guys have realized that zoom fit works pretty good. That's good and all, but that's not exactly what I'm feeling right now. Ooh, somebody's spiraling. Nope. Okay, it's going to be a limaçon. That makes sense. If I zoom in, boop, boop. I see 1 intersection, 2 intersections. This guy keeps on going. And then they come back again. If you guys notice my poor little circles, I don't know where they went. They disappeared. Remember, if you're bored, you should be silently working on the next packet. One more time. If you're bored, you should be silently working on the next packet. All right, 4th quadrant, right, guys? Nobody's in the 4th quadrant yet. Ooh, my 2 cosine theta is, but my other guy's not. My 2 cosine theta seem to be in the 4th quadrant between pi over 2 and pi. And he's going to be in the 4th quadrant again between 3 pi over 2 and 2 pi. And guess who's coming up at the same time? We could go ahead and zoom out our window just a little bit. Let me go ahead and try zoom fit. Is that zoom 0? Help me out just a little bit. Thank you. Let's see if that fits a little bit better. But as it does go. Area inside both. Did it say both? Shared? No, inside the limaçon and outside the circle. So inside the limaçon and outside the circle. Depending on who's in the woodshop, if you guys would have time, do you think you could break it down without breaking the boards so that we could store it easier? It might be too big of a job for today, but eventually that would be really helpful. Maybe possible, because you get like a crowbar and you could just, right?
Yeah, I could probably do that.
But if not today, it's okay. We can do it after spring break. Do you think you can? You think? Okay. Let me get those off. Here, I'll get the door for you though. Thank you. Praise the Lord. Okay. So you guys hopefully see the idea that we're going to have to subtract, right? A few people, when they asked me this, I guess just one person, when we talked about it yesterday, got a little confused by the bounds. However, if you notice, this guy went 0 to pi over 2, pi over 2 to pi, pi to 3 pi over 2, and 3 pi over 2 to 2 pi. So the nice thing is, when this limaçon got in the 4th quadrant, the circle was also in the 4th quadrant, which makes it a little bit nicer. And if you notice, remember, for area, can't we go out, right? So the whole area would be going to the limaçon, right? But we don't want the whole area. We want the in-between. So what are we going to subtract? the little one. So we're going to subtract the little one. So therefore, we're going to end up with the integral from 3 pi over 2 to 2 pi. Just because both of them actually end up being here at the same time. Otherwise, we would have to actually make it, like for instance, we could have made it for the circle. We could have made it pi over 2 to pi. It would have been the exact same area because it's covering the exact same region. But since they're both there at the same time, we'll use those as our bounds, and we'll go ahead and have 1/2 of the outer, which is our limacon, squared, minus the inner radius, which would be, did anybody plug that in and get it right? What was the final answer? Perfect. Does that make sense for 9? Okay. Noah, you had a question on 10? Okay. Oh, Lucy, you did? Okay. So then number 10, find the area outside the little loop, but inside the big loop. Now, if you guys think about this, this is going to be a limacon, right? And for our limacon, we could go ahead and just throw this in our graphing calculator. Let me get rid of that guy real quick. 1 minus 2 cosine. Zoom fit seems to be a good place to start, but you might need to zoom out a little bit. But I'll go ahead and just start there this time. It has an inner loop because the B is greater than the A. Ugh. I don't like them so much, but I guess that's okay. If you notice, this guy is really awkward in a sense. He started with the inner loop, and then he's going to end with the inner loop. Nice thing is that this totally is a unit circle value, even though it's a graphing calculator problem. So we could have set this equal to 0. Cosine is equal to 1/2, which is going to equal at both pi over 3 and 5 pi over 3, which makes sense because it happens in the first quadrant, and then it's going to happen, in the first quadrant, and it's not going to happen again until the fourth quadrant. Outside the little loop, but inside the big loop. Okay, what I saw was this graph started graphing right away, right here. Now, hold on. Some of you guys have realized that you might want to see it graph again. I think the easiest way I've heard so far is if you go back to your Zoom and then have it zoom again, like zoom fit again. Unless it doesn't work. There we go. There we go. So now I know exactly how it's starting from 0 to pi over 3. Couldn't I get this area from 0 to pi over 3 and double it, and I'll have my inner loop? Right? Hold on. All right. So from 0 to pi over 3, I have this. Right? I could double that, and I could have the entire inner loop, but I also need the outer loop, right? So from 0 to pi over 3, now I'd have to figure out, okay, well, hold on. How am I going to get this area? Sorry. So if I'm trying to get half of it and then double it, this area going to the exact same limacon, but for what range or for what value? Pi over 3, 2. How could you figure that out? When will this be maximized? Won't it be maximized? Like, you could graph this in function mode and find the maximum R value, or you could just say, wait a minute, won't it be maximized when cosine is -1? Because when cosine is -1, the maximum R is going to be 3. And that's going to happen when theta equals positive pi, right? So now I know, oh, okay. So half of the inner loop is from 0 to pi over 3, and then half of the bigger loop is from pi over 3 to pi. So far, so good? Okay. So then I can do the following. Can I erase the angles? Are we okay? So couldn't I do 2 times the integral from pi over 3 to pi, remember, times 1/2 of my limacon squared minus, so that's the whole thing. That's the whole thing. Now here's the dilemma. Why am I going to do 4 over 2? the integral from 0 to pi over 3 of the same limacel. Remember with polar area, if we're doing like one of those that starts at the pole and then does the inner loop later, remember how you have the entire area and then the inner loop is doubled? I need to not only subtract the inner loop, I need to subtract the inner loop twice, because the inner loop is not supposed to be included in this at all. What it wants is literally no inner loop, and the only way to get that is to not only erase it from itself, but also to erase it from the bigger. Hence why I have to do not only 2 to get out of the inner loop, but also 2 more to get out of the whole thing. Yeah. Right. But this region, oh, I see what you're saying. Hold on. I thought I was doing my entire interval, but I'm not. I'm doing from 0 to pi over 3. I'm doubling it. Oh, Lucy, my explanation, or those others who were listening, my explanation is if you did the entire interval, and I didn't do the entire interval. I did the interval disregarding the inner loop, so there's no reason for me to regard it twice. Good call. I purposely made those bounds, so I wouldn't have to double count it. I made it too hard. So for those of you that were following my logic, that would have been right if we had done the entire interval, which we could have done, which would have been 0 to 2 pi. If we had done 0 to 2 pi, we would have had to subtract him 4 times because the inner loop would have been counted and the entire interval would be counted. But I was being very careful to just get the inner loop and just get the outer, so there was no inner loop that was double counted. There you go. Final answer was? C. All right. Any more multiple choice questions? Oh, yeah, Dylan. 11. Common. Guys, we see 3-leafed rows that goes out to 4, right? With polar axis symmetry, and then we see a circle that's 2. Let me go ahead and get rid of all the smart ink. Let me go ahead and graph, zoom fit, 4 sine of 3 theta. Is this one that we did yesterday? Got it. Oh, yeah. Good question, Dylan. This one was rough. I'm going to be very careful with my bounds. Okay. Intersect. Intersect. How's that going? Let me go find those intersections real quick. Sine of 3 theta. 2 divided by 4. Sine is equal to 1/2 at pi over 6. 5 pi over 6, and, well, some more pi over 6s. Theta is going to equal pi over 18, 5 pi over 18. If I was to keep going, it's only for a second quadrant, so I would need to do 13 pi over 6 divided by 3, so that'd be 13 pi over 18. We can keep on going from there. Come back, calculator. I'll stop there. So then as we're looking over here, maybe you guys can see that the first intersection right here, which you could have actually graphed this in function mode. You could have graphed this guy as y1, this guy as y2, made your window 0 to 2 pi, and found the intersections. They would be sinusoidals, like it wouldn't look like this. If you could find the intersections, I did that. I think, Katrina, you and I did that, right? And we ended up getting, we ended up getting like 0.17 something, something, something. It was the exact same thing as pi over 18. So if it wasn't unit circle, you would graph it in function mode and find those intersections. But when you're trying to think about what's going on, okay, Here's how my brain thinks. I need the area common to both. I think, okay, if I'm doing polar area, what's the easiest one for me to visualize? That guy. That one's easy for me to visualize. I'm going to the rows, I'm going to the rows, I'm going to the rows, I'm going to the rows until right there, until the intersection point. And then I could go ahead and say, okay, now I need to go to the circle. My bad. Common to both. I'm going on the outer part, aren't I? I was thinking between. Lo siento. Okay. I'm going to the circle, going to the circle, going to the circle. Then I'm going to the rows, going to the rows, going to the rows. Now that's C starting here, but let's think going earlier, like from 0 to pi over 18. If you think about it, I am going to the circle, going to the circle, going to the circle, going to the circle. But then, between 0 and pi over 18, I'm going to the rows, going to the rows, going to the rows. So if you think about it, going to the rows will happen until pi over 18. Then going to the circle, then going to the rows. Now the problem is, to get just that one, which I'm going to then go ahead and multiply by 1, 2, 3, I have to do 1, 2, 3 different integrals. Or, here was my thought. Or you could go ahead and, why don't we just, I don't know, split this guy in half. Pretend that's in half. Split that guy in half. So what if I go from 0 to pi over 18, going to my rows, which would be my 4 sine of 3 theta squared. Then what if I add, going from pi over 18 to halfway in between, which would be 3 pi over 18 or pi over 6 of my circle. And what if I say, let's multiply this whole thing by halfway? 1, 2, 3, 4, 5, 6. Multiply by 6. Or you could have done 0 to pi over 18 of blue, pi over 18 to 5 pi over 18 of red, 5 pi over 18 to pi over 2, yeah, 5 pi over 18 to pi over 3. You would have had to find the zeros. Sorry, I didn't find the zeros. We could have come back to our 4-leaf rows and found the 0. And then sine of 0 would have been 0 pi, 2 pi, divide by 3, divide by 3, divide by 3. Yeah. Then 5 pi over 18 to pi over 3. And then multiply that by 1, 2, 3. No, that was my intersections. Sorry, I was finding my intersections. So these were the intersections, pi over 18, 5 pi over 18. The zeros, I didn't even solve for them. Does that make sense? Oh, because pi over 18 was the first intersection point, setting these two equal. Pi over 18 was the first, so that's where they hit. So as you go from, let me try to zoom in, Dylan, real quick. Because the picture is kind of zoomed out. I'm sorry. P.S. Zoom box is great. Zoom box lets you zoom where you want to go, though. So as I come from 0, I have to hit the rows until pi over 18. Then I have to go Because these were the intersections of the two curves. That's what those two were. And then could have done 5 pi over 18 to pi over 3. That would have been the way of doing 3 times. I guess we can pull out a half of everybody. So 3 halves. That would have been 0 to pi over 18 of, we'll call him R1 squared plus pi over 18 to 5 pi over 18 of R2 squared plus 5 pi over 18 to pi over 3 R1. So this is one way of doing it. I just stopped halfway at 3 pi over 18 or pi over 3, and I just did blue plus red, and I multiplied by 6 instead. Okay. Yeah, that visual one was really hard. I actually, Dylan, yesterday when John and I did it first, I didn't even think about this yet. I went to red, and I said red, 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 red. Uh-oh, blue, blue, blue. Oh, so backwards, red, 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 blue, 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 blue. Because it was hard for my brain to think of that too. So I went here first because it's easy, and then I realized, oh, some blue, forwards and backwards. Okay, that one was gnarly, that one was nasty. Hopefully that didn't get too messy with a really thick smartboard marker. Do you have any other multiple choice? Okay. FRQs, guys, I realize you have some questions. Let's go ahead and pause for a second so that I can go over. So you guys have the FRQ answer keys online. Yes, obviously I can maybe give some more clarification to that, but let's pause real quick. Spring break, let's remind ourselves. AP exam, we have the spring break memorization. Did Cameron check my box? Oh, no way. Do you want to go check? That should have been super easy to copy. Oh, you know what? BC's behind AB and they didn't split the copies. Don't worry, we're good. Okay, take one pass around, Eileen. The forever memorizing sheet, I am so sorry I didn't realize I had it, is coming around now. You guys know what to do with your forevers endeavors? One check means you quoted the whole thing, forevers and endeavors, one time. The whole thing one time. Handwriting the whole thing is worth 2 times quoting. Do the Monday we get back. It'll be shown on your homework calendar, and that Forever Endeavor quiz is on that Monday. You also have the practice exam due Tuesday, but obviously, do you want to save that practice exam till Monday night? No. The practice exam, not bonus, not optional, due Tuesday by the end of the day, which means I guess you could even be grading it during the day Tuesday. The answer key will be gotten up by the end. Did I give you guys just multiple choice? No. Okay, that's a bad 2003 copy. I'm removing this and getting you guys the full 2003. Good try. E for effort. So this packet, due Monday, going over questions after our Forever Endeavor quiz. And then these packets are done. No. This is not due Monday. This one's due the Friday after you get back. And if you guys notice, hold on. Do some of you still have AB from last year? Could you technically copy it down? Yes. But wait, doesn't BC start somewhere? BC starts, I think, around G. Ah, look. H, parametric and polar. I, vectors and vector-valued functions. J, Taylor polynomial approximations. K, infinite series. Anyway, Alan, was that yours? So could you copy down AB? Yes, it's up to you. Could you think through it again? Yes, but there's also BC stuff. But it's not due until Friday. Why Friday? What's Saturday? So I want you, after we get back from spring break. We've been talking about this forever. Okay. So April 14th, put it in your calendar. If you cannot make it, our plan is to take the makeup AP the next Monday, which is the 14th, 15th, 16th, which is when we were going to try to do the BCers helping me with the FRQs, but sadly, we have people literally who won't be in state Thursday or Friday or Saturday, so I'm trying to at least let them, the ABers, get some review for it before their mock AP. You guys know how it stressed you out last year. So we'll do the BC grading thing. We'll talk about it when we get back. The practice exam, totally mind if it's not turned in until Wednesday when we get back, but should you work on it somewhat over break? Yes. Kiddos, I'll just give you all hundreds on the polar area. Hopefully you deserved it. Hopefully you deserved it. I'll see you later. No confessing right now. Happy spring break. Bye, guys. Thanks.